So, hello everybody, thank you for the invitation. So I was asked to talk about the DEMETER spacecraft, which, as you know, was the microsatellite devoted specifically for the study of seismo-electromagnetic effects in the upper ionosphere. Now, why me? Well, I started university back in 2001, which is kind of like a couple of years before the start of the DEMETER. I started my first space physics project in 2003. It still wasn't DEMETER, it was cluster spacecraft and natural electromagnetic emissions, equatorial noise. But then I spent 2 summer stays in LPC-2E in CNRS in Orléans, France, in 2004 and 2005, which means basically just after the DEMETER launch, when I was supervised by Michel Parrot, and I eventually did a PhD under the supervision of Michel Parrot between 2007 and 2009. Now, Michel Parrot, he would be a natural person to speak about the matter in here. Unfortunately, or fortunately, whatever, he retired in the beginning of this year, so he wasn't able to deliver the talk. But he was the principal investigator of the DEMETER spacecraft, and he was also the PI of the surgical magnetometers on board. And he was generally like very, very interested in all natural and artificial electromagnetic wave signals observed in the Earth's magnetosphere. He was always willing to try the new things, new ideas. It's also why he was also able to push the matter for this seismo-electromagnetic purposes. And what I also admired a lot about him, he was always up to date with the literature, always reading all the new papers and always knew about everything which came up in the news. Okay, so enough for the introduction. Now for the scientific motivation of the DEMETER. Well, it was the spacecraft whose abbreviation means detection of electromagnetic emissions transmitted from earthquake regions, specifically designed and devoted to the study of seismo-electromagnetic effects, as is marked here in the list of scientific objectives. The primary scientific objective was to study the atmospheric disturbances in relation to the seismic activity and to examine both the pre- and post-seismic effects. In the same manner, it was also designed or intended to study the ionospheric disturbances in relation to the volcano activity, but also the other goals, eventually not related to earthquakes, but they also proved to be quite important, successful, was to survey the emissions related to anthropogenic activity and eventually globally contribute to the understanding of waves and situation in the upper ionosphere and magnetosphere. So I would like to underline that also the seismic effects were the primary goal of the DEMETER spacecraft. There were many other results obtained by the spacecraft mission. I will not talk about them here, but it was like really successful spacecraft, not only in the sense of seismic effects, but also globally in understanding the magnetosphere and upper ionosphere. Now, for the spacecraft parameters and some basic info about the mission, the spacecraft was launched in 2004 at the end of June, and it operated until the December 2010, which means something like 6.5 years in total. It was a microsatellite with the weight somewhat over 100 kilograms and placed on sun-synchronous orbit, making roughly 13 orbits per day, and the local times were just shortly before the noon and shortly before the midnight. I must say that this placement of the spacecraft into this sun-synchronous orbit, allowing basically to eliminate the local time from many dependencies, because you could easily distinguish just the daytime orbit and nighttime orbits, nothing in between. So it was quite useful for all or many of the further analysis performed. In total, it performed something like more than 30,000 of half orbits. By the term half orbit, it means you take the one orbit and you separate it to the daytime part, daytime half orbit, and nighttime part, that nighttime half orbit. And the measurements were performed essentially continuously at the geometric latitudes lower than 65 degrees. There were essentially no measurements at larger geometric latitudes due to the technical reasons. Now, there are 2 modes of operation, termed burst and survey. The reason for that basically was that even though the spacecraft was able to continuously measure, the capacity of the telemetry wasn't sufficient to transmit all the data to the ground. That means the survey mode data, the data with lower resolution, with some compression, lossy compression performed on board, were available basically all the time, but during specific time periods of interest, which by default were these seismic zones marked by the red on the plot on the right-hand side, but they could be eventually reprogrammed if needed to some different times and different locations. So during these specific time intervals, the burst mode was operating, and the more higher quality data, but also the data with larger volume were possibly available. Now, I just listed two links for the spacecraft. The first one is the link to the DEMETER Mission Center, where the data can be eventually got, at least in the form of quick looks. And the other one is some French archive where all the DEMETER data recently archived. Now, for the instruments on board, there were 5, or eventually 6, if we consider the neural network, 6 instruments on board. There were the instruments for electric, ICE, and magnetic field measurements, IMSC measurements. There was the ion analyzer for measuring the ion plasma and their composition. There was the energetic particle detector for measuring the energetic particles basically coming from the radiation belts, and Langmuir probe. There was also the neural network for the automatic identification of visitors, which were kind of deemed to be possibly also related, at least in some anomalous properties, and so possibly to the volcanic and seismic activity. Now a bit more detailed about the measurements. For the electromagnetic wave measurements, there were 4 different frequency ranges distinguished. In the ULF range, up to 15 Hz, both during the burst and survey, no matter what was active at the moment, there were the full waveforms of all the 3 electric field components available, and no magnetic field measurements were performed in this frequency range because it was the search coil not operating in these low frequencies. Now, in the extra low frequency range, up to about 1 kHz, during the burst mode, there were all the 6 waveforms of the electromagnetic field components available, which means you had 3 electric field and 3 magnetic field components, which allow to perform a detailed wave analysis, which means to determine both the polarization and propagation properties of the waves. So that was quite nice. It was limited by the burst mode coverage and by the frequency range only up to about 1 kHz. Now in VLF range, up to about 20 kHz, determined by the bandpass filter, but since it wasn't like there was some fall down of the efficiency, so that the strong transmitter signals even above 20 kHz could eventually be measurable due to the aliasing. But basically the upper frequency limit of this range should be 20 kHz. And in there, during the burst mode, the waveform of 1 electric, 1 magnetic field component were available. And during the survey mode, there were the spectra calculated on board and some frequency and time averaging used. So it was still 1 electric and magnetic field component, but the frequency and time resolution were kind of predefined and determined by that onboard spectral analysis, with the frequency resolution something like 20 Hz and time resolution something like 2 seconds. Now, it's also worth to note that the magnetic field data on board DEMETER, they suffered quite a lot from onboard interferences. So for many purposes, people did opted to use the electric field data instead. Then in the high frequency range, which means up to about 3 MHz, during the burst mode, there were occasionally available the waveforms lasting something like 1 millisecond. And during the survey mode, it was only onboard calculated spectra with rather poor frequency resolution, but still eventually useful. Now for the plasma measurements, the ion analyzer, it provided the measurements of density, temperature, and velocity with the time resolution of something like 4 seconds, and it could distinguish between the 3 ion species, hydrogen, helium, and oxygen. The Langmuir probe, it also provided this time electron density and temperature, but it should be quasi-neutral so that they should kind of match, which was not always the case, but at least roughly. And the time resolution was better. It was basically 1 second. Now, for the energetic particle measurements, the energy range between 70 keV and 2.5 MeV was covered. In the burst mode, the time resolution was something like 1 second and 256 energy channels, linear energy channels. In the survey mode, it was just half of those energy channels, and the time resolution decreased to 4 seconds. But anyway, both the time and energy resolution of the performed measurements was pretty nice and allowing many different studies related not only to the seismic activity, but also to the radiation belt dynamics and so on. Now, the last one, that neural network, which was quite amazing, they managed to do it in the beginning of 21st century, basically, was the neural network on board implemented for the identification of lightning-generated whistlers. Basically, the idea was that to run that identification, you need to have the high-resolution data, which can be transmitted to the ground in full resolution, so that you need an algorithm implemented on board to look for these whistlers. And they really managed to do so somehow. And for each 0.1 second long time interval, the algorithm provided basically the number of whistlers detecting during that time interval and their dispersion class. It didn't work completely flawlessly, but it was kind of like nice experiment. Okay, so that was a general introduction to DEMETER, and now I try to pick a bit of the seismic related results and some thoughts on them. So first, some general thoughts. Well, at least from my point of view, the own existence as well as the possible mechanism of generation of such effects are still quite unclear. I strongly believe that a case study cannot in principle confirm or deny the existence of such effects. So I think that the only way to really prove or eventually disprove them is to use statistics, which, as far as I know, is still kind of clearly needed. Now, why to do this on the spacecraft and not on the ground? Well, the clear advantage of the spacecraft is that a single instrument or single spacecraft can, in such a case, cover the entire Earth's surface, more or less, even though not at the same time. And it can thus get into the vicinity of many earthquakes, even though not at the same time delay from the main shock. Now, the problems when using the spacecraft for such a purpose, obviously, it's you need to face the strong natural background, which strongly varies as a function of many different parameters. And moreover, the signal, whatever it might be, needs to propagate through multiple layers before eventually reaching the spacecraft. Now, kind of related to that, it's even not quite clear, at least not to me, what should be, for example, considered like the distance between the spacecraft and the earthquake. In another case, in other words, what point on the Earth's surface a spacecraft located in this region or this point would see, if it would be A, corresponding to the vertical propagation, or the point B, corresponding to the propagation of the magnetic field, or even some propagation of whatever signal from the opposite hemisphere. It clearly depends on the mechanism which we eventually expect to happen for any effects observed. So that's one clear complication. Now, how to account for the natural vulnerability and that strong natural background that I mentioned? Well, there are several options that I do see, and we eventually opted for the last one that I will try to demonstrate here. Well, the first one is that you might possibly try to somehow compare the situation close to and far from the earthquake. But when using this for the spacecraft, it's eventually quite problematic, because the natural background itself can strongly depend on the position. And for example, if it changes as a function of latitude, which will often be the case, then this close to and far from difference doesn't really need to be so clear and to prove anything. Then you could kind of perhaps try to check for the number of values exceeding some predefined thresholds and whether this number somehow changes around the times of the earthquakes and in their vicinity. But the problem with this is that the own definition of such thresholds is clearly rather arbitrary and can significantly affect the results of the analysis. Now, the next possibility might be possibly to use some control orbits, which means you might try to contrast the data measured during the orbit passing nearby the earthquake with the data measured before or after. But the problem is that it's kind of difficult, I guess, to be aware of all the possible biases of this analysis. Most importantly, it's never the control orbit by definition. It's never exactly the same location and the same conditions, right? So it's like kind of difficult to contrast it properly. Now, perhaps the best way how to deal with this occurs to me that it would be to kind of calculate the difference from some mean values, and express them in a number of standard deviations. The idea for this would be basically expressed by the sentence that when we want to find out what is exceptional in some way, we must know what is normal first. Now, this would require the data processing in 2 steps and obviously a large amount of data to be measured. In the first step, you might calculate the mean value and standard deviation at a given place under the given conditions of the values measured of whatever quantity. And then in the second step, you might evaluate the data measured at the time of the earthquakes and contrast them with the normal or long-term situation. Now, the problem with this is that the distribution of the values, no matter what quantity, is hardly ever Gaussian-like. So to use the moment of standard deviation to characterize it is not a very, very good choice. So how to deal with that? We basically define something called normalized intensity. The idea was pretty simple. We used basically the full histogram to represent the distribution of the measured quantities. And then instead of using the standard deviation, we simply checked what is the corresponding value of the cumulative distribution function. That is the probability that you would just measure such value or lower by coincidence, or that we correlate as the cumulative probability. Then what we can do is we can take these cumulative probabilities measured, let's say, in the vicinity of the earthquakes, which means both in time and both in distance. And then we can somehow calculate the mean of these cumulative probabilities. We can subtract 0.5 just to make it centralized around 0. And the nice thing is that statistically, the resulting distribution would be the Gaussian distribution, the normal distribution, with the mean value of 0 and some standard deviation. Now, to determine the standard deviation, you can basically use the central limit theorem to determine this. But the point is that you would need to know the number of independent samples, which is quite tricky to determine. Like, you can kind of guess that the lower estimate of that number of independent samples would be the number of orbits in that particular bin. But to do it more properly, you would eventually need to use the Monte Carlo simulation for that. But if you do that and you determine the standard deviation in a particular bin, you can normalize by that and you get the Gaussian distribution with the mean value 0 and standard deviation 1. And it allows you to systematically evaluate changes related to anything, let's say in earthquakes, to earthquakes in this case, and moreover, to determine the statistical significance of these observed variations. And here's an example of the results that we eventually obtained coming from this 2008 paper, where we checked this normalized probabilistic intensity, which means directly expressed statistical significance of the observed effect. Now, it's for electromagnetic waves. The blue corresponds to the decrease of the wave intensity. Red corresponds to the increase of the wave intensity. On the y-axis, there is the frequency. X-axis is the time from the main shock. And it used only the earthquakes lower than 40 kilometers and spacecraft measurements within something like 3 degrees and nighttime only data. So basically, the only effect that we eventually observed was the change of the wave intensity shortly, something like 0 to 4 hours before the time of the main shock, in the frequency range close to 2 kilohertz. And it corresponds to the decrease of the wave intensity. Now, this was eventually confirmed later by the analysis of my colleague David Pisha in 2013, where he used all the database of the DEMETER earthquake data and DEMETER data available during the intermission. And then it confirmed this decrease of the wave intensities at frequencies about 1.7 kilohertz shortly before the time of the earthquakes. And quite nice plot, which I do like, is this plot on the left-hand side, which shows the evolution of this during the DEMETER mission. So you can see that the effect, which was there basically during 2008, it didn't get so much more significant during the later years, which is still kind of puzzling. And to me, at least, it kind of undermines my certainty about the significance of that. Anyway, it seems to be just for the stronger earthquakes. And what may be possibly the explanation for that, and why just 1.7 kilohertz? Well, the reason might be the Earth's ionosphere waveguide cutoff frequency. The point is that we have the waveguide between the Earth and ionosphere, which has some specific frequencies. And essentially what you do observe that the waves at frequencies above 1.7, they can propagate quite freely in the waveguide. And they usually do have the large wave intensities because of the lightning. It can be seen in these plots, the general plot and the zoomed one at the bottom. Now, the point is that if you would have some change of, let's say, ionospheric densities related to the earthquake activity, then the characteristic frequency of this waveguide change, and as a consequence, you would have the change of the observed waves. So it would be kind of the indirect effect related to the change of the waveguide. Now, I have a couple of more minutes.
Can you wrap up soon?
Yes, just 2 more minutes, perhaps. It's the ionospheric density. So that was the waves. Now, for the density, there are case studies showing some possible changes of the density around the times of the earthquakes. And there was the statistics by Jan in 2017 about the statistics of the density, basically the same one as I showed before for the waves, this time for the density. And it showed some kind of clear effect after times of the earthquakes, but nothing so clear before, at least for me. So there was the ionospheric density changes. And then we had a study corresponding to the changes in the transmitter signals. Basically, we checked the signals detected by the DEMETER coming from the VLF transmitters and possible changes of these transmitter signals when the earthquake was nearby the geodesical path. And it seems to be kind of, again, the decrease of the wave intensity, possibly the same effect as I demonstrated before for the arithmetic waves. Okay, so my conclusion, just very briefly, I guess the DEMETER can be considered very, very successful, not only for the seismic-related phenomena, but also for anthropogenic and magnetospheric. And for me, the main issue with the seismic-related signals is how to account for the varying background and identify possible small seismic effects, which I believe is extremely tricky. And so far, at least as far as I know, and as I understand that, the existence of these seismic-related effects, and in particular the precursors, is still very, very questionable. And it's always, in all the studies I saw, basically on the edge of the statistical significance is properly evaluated. Still, I believe it's very, very scientifically tempting and interesting. Okay, thank you.
Thank you, Professor.